Hi, chemistry. We're going to take a closer look at how the particle models for temperature, pressure, and volume line up. So as we look at this, these models, A, B, and C, what you should look at are the temperature changes that are occurring, the volume changes that are occurring. Both of these are going to show up in the model. Remember, temperature is going to show up as arrows. The bigger the arrows, the higher the temperature. Volume is going to show up as the size of the box. The bigger the box, the bigger the volume. Now, temperature and pressure together lead us to this conclusion of pressure. And when you think of pressure, I want you to think of the word collisions, because anytime pressure increases, it's increasing because of more collisions or harder collisions. And that's really the key here. So as we look at each one of these boxes, we're going to look at how temperature and volume are changing, and then we're going to draw a conclusion as to how pressure is changing. So in this first box, you should be looking for, are the arrows changing between the start and the end? And in A, they are. The arrows are getting longer. So temperature is increasing, and that means we're going to have more collisions and harder collisions. Volume is not changing, so I'm just going to put an X there, which means we don't have to consider volume. If temperature is going up and we're getting more collisions, that's going to lead us to more pressure as well. If we look at box B, we can do the same thing. Now, box B would be a good place for you to pause this video and think through these concepts on your own. When we look at box B, we can see the arrows are getting longer, so temperature is going up. That means we're getting more collisions. Our volume box is also getting bigger, so volume is going up. When volume goes up, if the same amount of collisions are happening, then they're going to happen over this wider area. It's kind of like if you're hitting the table one time every second, and all of a sudden you have to hit two tables one time every second. Well, each table will have less hits or less collisions. So we can write that down. And that's going to lead us to a lower pressure. So here we actually have more collisions happening from temperature, leading us to a higher pressure, but less collisions because our box is getting bigger. So we have two contrasting patterns for pressure, and we actually don't have enough information to know if this pressure is going to go up or down. So for now, we can just put an X there. Pressure, as far as we know, will stay constant until we know which one is dominating the conversation, temperature or volume. So we're going to assume pressure is constant in box B. And then we can look at box C as well. We can see the arrows in box B are box C are roughly the same size in the beginning and the end. So temperature is not changing. Temperature here is constant. Volume is getting bigger. Our box is getting bigger. And that means we're going to have less collisions happening. If we have less collisions happening, then our pressure is going to go down. Now, in addition to thinking through this through the particle model, a good practice is to go through and look at this in the graph model as well. So I'm going to draw a graph for each of these three, and then we're going to think through what should be on our axes. So here in box A, temperature is changing, and as a result, pressure is changing as well. So we can look down here and look at which graph has temperature and pressure. That would be this second one, Gay-Lussac's law. Temperature goes down here, pressure goes on the side here. And temperature is increasing, right? So I know that we're going to go this direction in temperature. My pattern here is proportional. So if I'm moving to the right on the x-axis, I'm going from a low pressure to a high pressure. That's what we said over here. Pressure is increasing. And now we can explain it from a particle model perspective. We can also explain it from a graphing perspective. Okay, let's look at box B. This would be a good time for you to pause the video and see if you can walk through the explanation in the graph yourself. So in box B, remember we have temperature changing and we have volume changing. So we can go down and look at which graph has temperature and volume on the axes. That would be Charles' law. Temperature is X, volume is Y. I can put temperature down here as the X, volume is the Y. Charles' law is a proportional pattern. I'm just going to sketch that. And then temperature is going up, so I should be moving this direction on the x-axis. Volume's also going up. So I would be moving this direction on the y-axis. Now, where does pressure come in here? Remember, pressure is the one we're trying to draw the conclusion on. Remember, pressure is not in this math model. We have no P here. That's because pressure is our constant. Pressure is your slope. And since slope is the same in the beginning, slope is the same in the middle, slope is the same in the end, or the angle of our line is the same in the beginning, angle of the line is the same in the middle, angle of the line is the same at the end. Pressure here is our constant. Pressure is constant in this model. So that again lines up to the conclusion that we drew from our particle model. Okay, let's look at this last one, C. So our two factors we're looking at are volume increasing and pressure. So volume and pressure is our third pattern. That's Boyle's law. Volume's on the x-axis, pressure's on the y. Our graph shape is here. So if volume's increasing, I'm moving left to right. And as I move from left to right, my pressure goes from high to low. My pressure should be decreasing. Again, I can explain that in terms of particle models. I can explain that in terms also of my graphing model. Okay, so take a look at the next couple questions for this, and then go ahead and try the practice quiz.